So this video is in relation to fuels and heats of reactions. So this is an area of chemistry got to do with the burning of fuels and then the heat given off or the heat taken in during chemical reactions, and we'll study some of that. This video is just an introduction to the hydrocarbons, and we'll go as far as homologous series, and then we will move on, or we'll leave it at that for this video. So the introduction to organic chemistry, first of all, that's effectively the branch of fuels that we're going to look at. You can also use inorganic compounds like hydrogen as a fuel. We're going to focus on organic chemistry. And effectively, organic chemistry was originally thought of as the chemistry of chemicals made by living things. But then urea was synthesized in a laboratory. So then that's an organic compound that's produced by living things, the breakdown of proteins. So instead what we had to do is we had to rename organic chemistry. It was renamed then as the chemistry of compounds that contained carbon. So a lot of the time people think of organic chemistry as carbon chemistry. It is true to say that plants, coal, oil, animals, all of these things are organic compounds in the more traditional sense, I guess, when people talk about it. But just remember that when we say organic chemistry, we're talking about carbon chemistry essentially, historically, even though it would have been different. There's proteins, they're organic, carbohydrates, fats, these are all examples. Fats and oils are. Inorganic then would be things like salts, water, oxygen. Now, there are some inorganic compounds which contain carbon. Carbon dioxide is an example of that. Carbon dioxide would be considered to be an inorganic compound. However, or something like carbonic acid as well, which is effectively rainwater, would be considered to be inorganic as well. But the vast majority of compounds that contain carbon are considered to be organic compounds. Frederick Walter, that's the guy who synthesized urea in a laboratory. This is what urea looks like. You get used to these models. There you have carbon. Carbon is normally represented as a black sphere, and the blue here represent nitrogen. The grey, the little small grey ones, represent hydrogen, and the red one represents oxygen. And that's essentially the compound that is urea. Organic, yeah, so that's why we had to move on. And organic chemistry now, you may assume, is the chemistry of carbon containing compounds. The extent there's such a wide variety, a big thing in organic chemistry is trying to classify organic compounds. We'll run through some examples of organic based substances now. Maybe some you'll be familiar with, some you might not think are organic, but we want to run through them now briefly. Coal, natural gas, petrol and wood. Remember, coal, natural gas, petrol, they all come from essentially dead plants and animals that have been put under a great deal of pressure over a very, very long time underneath the Earth's crust, whether that's solid crust or indeed oceans and sediment. But these are obviously considered to be non-renewable because of the length of time it takes to produce them over very, very long periods of time. Drugs, things like aspirin, quinine was used, chloroquine, and that was used as an anti-malaria drug for a long time. I think it's not used quite as much anymore. Morphine is an organic compound used to treat pain, and cocaine is an illegal substance as well. And these all have a role in interrupting the nervous system, affecting the nervous system. Explosives, things like dynamite, nitroglycerine, TNT, cordite, these are all examples of organic compounds that are highly explosive. So some are very, very dangerous, very, very difficult to handle. Things like poison, cyanide and strychnine, these are examples of organic compounds that are poisonous. Dyes, indigo is used, or sometimes it's used in clothing, or it's used in dyeing fabrics and that. Synthetics, things like nylon. Now these are synthetics as in man-made. They're synthesized, so there's the word synthet. And the synthetics like nylon, these are all examples, and acrylics, these are all examples of things that are made by humans from organic compounds, and majority of these are actually made from the products of refining crude oil. The same for plastic, actually, polyethylene or polythene, bakelite, PVC, polyvinyl chloride, polystyrene. These are all examples of organic compounds, and again they're derived from the products of oil refining, fractions within oils, and then manipulating them into things like plastics. Household paper is an organic compound, always comes from trees, woods, cotton, wool, glycerine, olive oil, Vaseline, soap, turpentine. These are all examples of compounds that are derived and contain carbon. Why is carbon so special? First of all, if we look at the idea that carbon is a in group 4 in the periodic table. Now if you think about electronegativity in this, with group 4 elements, you need to remember that on the outermost shell, like we have the inner shell here of carbon. The carbon comes in there, so it has those two inner electrons. But like a lot of the time in chemistry, as you go through and as you leave junior cert and you're leaving cert and going to college, I mean, the inner electrons aren't normally drawn. I mean, there's no benefit to drawing them there because they aren't involved in bonding, essentially. It is only the outermost electrons. So a lot of the time, people will tend only to draw the element or the electrons in the outermost shell. And you get more and more used to that. So instead of drawing that, the inner ones, and then the 4, a lot of the time we just draw the carbon and then mark in the 4 outermost ones, if you like, and there you have 1, 2, 3 and 4, and that's the carbon. Now what makes it so interesting is that it has an electronegativity of in or around a value. If you look it up in the periodic table, carbon's electronegativity, it has a very central electronegativity. And what I mean by that is, for it to share a pair of electrons, remember that the electronegativity difference is what's important between atoms. So if an atom has a large electronegativity difference with another atom to which it is bonded, then it is considered to be a greater tendency to be an ionic bond. Whereas in the case of something like carbon, because it is in around, we just find the exact value there, 2.1, 2.4. So carbon comes in there at 2.4. So carbon has an electronegativity, if we use Pauling scales, it has a value of about 2.4. Now because it's 2.4 means that, you know, the max on the Pauling scale is 4. And we're talking about min values there, considering, because obviously every atom has some electronegativity of 0.7. That's down in the group 1 elements. You see, you're never going to have atoms that are very, very far away. I mean, if we went all the way up to 4, in the case of fluorine, we'd have a difference there of 1.6. If we went all the way down to 0.7, we would have a value of 1.7. So, you know, there's always, even, and remember that they're the extremes now, they're like the max differences. Most will lie much closer, or, I mean, the only one with 4 is fluorine, and carbon can actually form a bond with fluorine, covalent bond, I mean. And then in the case of going all the way down to the group 1 elements, so you always, like, there's an awful lot of atoms that will form either a pure covalent or a polar covalent bond with carbon, rather than having electronegativity of greater than 1.7. Remember that if it is greater than 1.7 or equal to 1.7, we consider that to be an ionic, or at least we tend to believe that will in fact form an ionic bond. So mostly organic. The point being here is that carbon has a great ability to form covalent substances with so many atoms in the periodic table. And that comes back to electronegativity. And we should always think about that when we're studying chemistry. I mean, so much chemistry goes back to the principle of electronegativity. I mean, it's a lot of the time, it's why all of the time effectively, why a molecule would be polar or non-polar, why a bond would be polar or non-polar, why a substance would be a gas, a liquid or a solid at room temperature, or at any temperature for that matter. So that type of thing is very important to try and link together as you're studying chemistry. But in any case, it has a great ability to share, and there we have a covalent bonds to gain the octet, and that again is just to fill, we're leaving certain A's, so you can think of it filling, it fills the 2s2, and then it fills the 2p6. So it'll fill up those, bring you all the way up to a full second main energy level, being completely filled when it shares another 4 electrons. That would be the full, and of course for it is 2s2 and then 2p. If you think about the electron configuration, it would be 1s2 and there's 2 electrons used there. That 2 stands for those 2 electrons. 2s2, and that brings us, we have 4 electrons used, and then we'll have 2 left to go into the 2p. And obviously we would need 4 to fill the 2p sublevel, and hence filling the second main energy level and the stability associated with that. And its outer electrons are involved in this bonding, and there are no lone pairs. So the shape of the carbon would be tetrahedral. You'll have a carbon, if it is bonded to 4 different atoms, that is, you'll have 2 atoms going away from the carbon out towards the back, 1 in the same plane, and then 1 would be going coming out towards us. Actually, those two triangles denote going away, and then this one would denote coming towards us. But in any case, we'll look at that later. This is an example of carbon in a bond with 4 different hydrogen. Hydrogen obviously is number 1 in the periodic table, therefore it would of course have just 1 electron. That's the 1s1. So it has 1 electron in its outer shell. To fill the first main energy level, obviously you only need 2, because of course the first main energy level is just the s orbital. So you'll have 2 electrons shared in this compound. I change the color there. Well, 2 electrons here, 1 from the hydrogen and 1 from the carbon, and likewise here, 1 from the carbon and 1 from the hydrogen, and it goes on, and you end up with this tetrahedral shape. You see 1 coming out towards us, 1 going away from us, or 2 going away from us, and 1 in the same plane. So to look at that as a molecule, this tends to be what is used to denote, like I said, most of the time carbon is what's used to denote a carbon atom is a black sphere, and then it has 4 single bonds. It would have 1, 2, 3, 4, and remember, bonds are made out of electrons. Therefore, if the bonds are made out of electrons repel each other. And this arrangement, which you know is tetrahedral, achieves a maximum distance between the bonds. And that's why you end up with this shape. And then a lot of the time the carbon atoms or the hydrogen atoms will then, again, we've looked at this before, but as carbon atoms will be bonded to 4 hydrogens. Hydrogens tend to what tends to be used is a light grey colour, or in this case a white colour, and there you end up with a tetrahedral shape. So that would denote that diagram there, 1 coming out towards you, 2 going away from you, and 1 in the same plane. tetrahedral, tetra there standing for 4. They are 4 sigma bonds because the orbitals head-on overlap. That's something else you can note as well. Carbon another very useful thing with carbon in terms of building molecules. A lot of the time I think of it like connects. It's so good. It's like the central thing in connects. It's so good at joining many different things together, including itself. So it bonds very well to itself, and here you see a carbon-carbon single bond. And that's the, if you like, the more elementary diagram, but normally we just draw this, and these lines indicate, like that line would indicate that there's 2 electrons being shared, a bond effectively. Carbon also readily forms double bonds with itself. There's a carbon-carbon double bond. Again, that would stand for 1 electron, 1 electron, 1 electron, 1 electron. So there's 2 pairs of electrons being shared there. 2 electrons from this carbon and 2 electrons from this carbon. And then likewise, down here you would have a sharing of 3 pairs of electrons. 3 from that carbon and 1, 2, 3, 3 from that carbon. And then remember, it's in group 4, so then it would still have 1 bond to make. Both would still have 1 bond to make to some other atom, given that the maximum there of 4. Carbon can form very long chains. This is one of the very useful things about carbon. Now, carbon-hydrogen, if you looked at the electronegativity values for carbon and hydrogen, hydrogen comes in there at about 2.2 on the Pauling scale, I should say. And carbon comes in again roughly around 2.4, 2.5 there, depending which table you look up. So let's just put it in 2.5, 4. So it is quite a close, or a very, very close electronegativity values there. That effectively means you get non-polar bonds. Perfect sharing there, perfect sharing there. So that's a very long molecule that is effectively non-polar. But don't forget that there's still lots of electrons involved in this molecule. So electrons will slosh over and back, giving rise to temporary negative ends and temporary positive ends. And then if you look at this, actually this is an added complication here. This would always be slightly negative, this end of this molecule. You have a carbon bonded to a double bond. Oxygen comes in there with a value of in or around 3.5, you see. So there's a bit of an electronegativity difference between 3.5 and 2.4. You have a difference there of 1.1. So the oxygens will be slightly negative. That should be a negative. And likewise here, slightly negative. And that will give you a slightly positive hydrogen here. And that effect, that's an interesting one actually. That's an example of what's known as a carboxylic acid. But in any case, what I want to get across here is can form very, very long chains. And obviously can bond to things like oxygen as well. This is a much simpler molecule. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 carbons. And then off each of those carbons you have 4 bonds. The terminal ones will be CH3, quite simply because one of its bonds is bonded to another carbon, then it has 1, 2 and 3 different hydrogens, and then you'd have CH2 here, and then it's CH2 all the way along, and it's 14, so it would be called tetradecane. Now we'd never look at that in leaving cert, but just to give you an example of a very big organic, tetra being 4 there and decane being 10, giving you a total of 14 carbons. The reason it ends in A and E is something we'll look at in another video. Carbons can form ring structure. This is an interesting thing about them, that they can form ring structure. So at each juncture here, you see these diagrams started a lot of the time in maybe more advanced textbooks than that, but there's carbons at each of those junctures. And if there's nothing else drawn in, you may assume that each carbon is saturated. That means it is a maximum of 4 bonds to 4 different atoms. And what they will be in this case is hydrogen when it's drawn with nothing written there. If there's nothing written there, you may assume that it's CH2. And you see there you get a cyclic structure in that it is around. And that's where the cyclo comes from. So cyclopentane. Now I don't know if you know the prefix pent, but pent stands for 5. So you count that, 1, 2, 3, 4, 5 cyclopentane. Here cyclohexane, 1, 2, 3, 4, 5, 6. Cyclo for the cyclic part of it, hex for the number 6, and ane because it's all carbon single bonds. It's difficult to get much smaller ring than cyclopentane because the ring will break open. Because remember, these lines represent bonds, and bonds are made out of electrons, and electrons are pale electrons, so you can never force them very close together. They become very unstable. I wouldn't worry with these bottom two for now. These bottom twos are what are known as organic. They have a special type of bonding where the double bond is, these three double bonds actually are spread around all 6 atoms. So it's not like that's a single bond and that's a double bond. It's more that they're all the way around, or halfway between a double and a single, which is interesting. But in any case, we'll look at that another time. As well as the above, carbon can also form single and triple bonds with other elements. There's a carbon double bond to oxygen. There's a carbon single bond to oxygen. And there's a carbon single bond to carbon. You see, when it keeps going CH2, 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 rather than writing that all out, you can just put CH2 in a bracket and then put a 16 there. Now this is the start of this chapter, so don't let it overwhelm you. This is just an introduction to the principles of organic chemistry and how molecules are made up. So little things like this perhaps are useful if you see that anywhere, and it won't look as quite as strange to you. Hydrocarbons then are compounds that only contain, pretty straightforward, hydrogen and carbon. And again, remember that hydrogen is grouped, we looked at this initially there, hydrogen has 1 electron, it's the 1s. To fill the 1s you only need 1 more, and that's a high degree of stability associated with that, and that's why it obviously creates that covalent bond. And as you can see, there's a good chance a single bond will be made between the two of those, and then that's a single pair of electrons making that, and then you would have 4 other atoms off the central carbon, and if it's a hydrocarbon, it would be that. Hydrocarbons are excellent fuels. I mean, this is something that goes back in history. People burning things like kerosene, for example. Kerosene is a hydrocarbon. It can be burned in air to release energy, and that energy initially obviously was used for light, and indeed just for, quite simply, heat. People throwing wood into a fire was essentially burning a hydrocarbon. The amount of energy has got to do with the type of bond that's involved. Not all bonds release the same amount of energy, or indeed the energy is actually released when the bonds are made in the products. So I think sometimes that's something that people aren't 100% sure in chemistry, that it's actually when the bonds are made that the energy is released. It's a lowering of energy, and the energy is released to the surroundings. I mean, the energy is not destroyed. But we looked at reaction profile diagrams before, but essentially in this case it's an exothermic reaction where there's the reactants, then you would have the activation energy, and there you would have the products. So there's the products and there's the reactants, and as you go forward, you see, look at delta H, or the heat lost in a reaction. This would be known as delta H. Now we will look at this again later in this topic if you like, but just to be clear, that the energy is actually released when bonds are formed in the products. I think a lot of people are not sure about that because they start talking about energy being released when these bonds are broken. A lot of the time to break bonds you actually need to input energy, so that'll be something like striking a match. Now that's fairly for leaving there, whether or not we'll dwell on that too much is maybe not overly, but it is the correct chemistry. So you should know the correct chemistry. The energy is released when the bonds are formed in the products, not when they react. Obviously, to break any bond, you require energy. So you should think about that. Don't worry about this bottom equation here for now. And the energy is used to break the bonds. Like in the case of oxygen, and this is something you do for junior cert as well, when you burn a hydrocarbon essentially, and then you collect the products and you pass the if you like, the what is given off from burning a candle. I think you use in junior cert. You use that and you pass it over cobalt chloride, or you pass it over blue or white copper sulfate, it'll turn blue. So water is a product when you burn hydrocarbons. And carbon dioxide, I think you pass the product, or the what's released from burning the candle at junior cert, you pass it into lime water essentially, and that lime water turns cloudy. And that's actually got to do with, lime water is actually calcium hydroxide, and when you put calcium hydroxide, it's just CaOH2. So calcium hydroxide, when it is or when you burn it in, or my apologies, when you pass carbon dioxide through it, CO2, and when you pass that through that, you get the white thing that's out in the burn in County Clare, which is of course calcium carbonate. And calcium carbonate is a white solid, and hence you get, or it's suspended in solution at least, so you get calcium carbonate, which is of course insoluble in water, giving you the cloudy appearance. Now that reaction, talk about that reaction a good bit in Leaving Cert Chemistry, so we're introducing it now, but just to be clear why that is the case. And then there's more water and carbon dioxide formed, and depending if you have sufficient oxygen formed, we talked about this before as well, you might not even be able to make carbon dioxide. You may make toxic carbon monoxide, and that's what happens when you burn a hydrocarbon in a car engine. Here's an example of some of the energy released in different bonds. You see as you burn. So this is kilojoules per mole. You know, in chemistry we always talk about per mole, because amount means a lot more to us in chemistry than mass a lot of the time. I mean, the only reason we use mass is so that we can determine the amount. Essentially the same as when you go into a bank with coins and they put it on a mass balance. Really they want to know the amount of coins, not the mass. And it's the same for us in chemistry. So per mole, remember, is just 6 times 10 to the 23 of those bonds in this case, or whatever you're talking about, chairs, tables, cats, dogs. In this case we're talking about the amount of bonds, and just remember that. Now, we'd never use mole for cats or dogs or chairs because there just isn't anything close to it on the surface of the earth, and the numbers of those, of course. You still could use it, but it'd be a very small decimal, I should say, of a mole. There's a carbon-carbon. You see, it's not exactly double, which is interesting. The reason for that is that one of those bonds is a sigma bond, and one of those bonds is a pi bond. So essentially, in one of those bonds, the electrons are directly between the two carbons involved in the bond, and in the other one, the electrons are actually slightly above. And again, that's for the same reason that when those two p orbitals overlap, they can't come down on top of this first bond, if you like, the sigma bond, quite simply because electrons repel each other. Nothing more complicated than that. And likewise here, you would have only one sigma bond, and then you'd have one above it overlapping, and you'd have one below it overlapping, and then you would have the sigma bond, which would be the more difficult bond to break. The pi bonds are always a bit easier. It's a bit like pulling tug of war. If you're stretching above your core or below your core, it's never as strong as if you pull a rope, let's say, as the center of your core. And that's the same principle in the case of a triple bond, indeed any of these double bonds. And there's a carbon-hydrogen bond, 113 kilojoules per mole. If you were to break 1 mole of the bone, 1 mole of the bonds, that's the amount of energy you would release. And then look at the amount of energy required to form these bonds. A carbon-oxygen bond, you have 743 kilojoules per mole. Remember, joules is just a measure of energy, and kilo is 1,000. So you see that in the side of food packaging as well for energy. And there's an oxygen-hydrogen bond. A homologous series. In order to study the vast and varied number of hydrocarbons in organic chemistry, they've come up with essentially families, much like you would have families in biology, or indeed species and Within species, then you'd have subgroups. Well, it's actually the same principle in chemistry. We have homologous series, families effectively, that adhere to some general rules. You see there's general rules. And then they normally have some distinct characteristic. Like for an alkane, it would be single carbon-carbon. All the carbon-carbon bonds are single bonds. For alkenes, you have carbon-carbons with double bonds. You have alkynes, which are not here, carbon-carbon triple bonds. Alcohols have a carbon bonded to an oxygen bonded to a hydrogen, or the hydrox, this OH group here. And then you would also have that member there, which is carboxylic acid, and you would have a single bond to an oxygen, which is a single bond to a hydrogen, and then you have a single bond, or double bond I should say, to another oxygen, and that's why it's written as COOH. CO is that one, if you like, and then this OH is down below, but both of them are off the same carbon, the double bond to the oxygen and the single bond to that OH group there. And that should be sufficient. Now this is really just an introduction to organic compounds. We will the next video we will look at a much more. We'll go through some of these families of organic compounds that are used as fuels.